Where does power consumption go in a computer? Today we had a weird discussion over lunch. What exactly causes power consumption in a computer, particularly in the CPU? Ada, for obvious reasons I don't need an explanation why a hard drive, display or fans consume power. The effect there is pretty obvious. Figures you usually see indicate that only a percentage, albeit a large one, of the power consumption ends up in heat. However, what exactly does happen with the rest? A CPU isn't, anymore, a device that mechanically moves parts, emits light or uses other ways of transforming energy. Conservation of energy dictates that all energy going in has to go out somewhere, and for something like a CPU I seriously can't imagine that output being anything but heat. Us being computer science instead of electrical engineering students certainly didn't help in accurately answering the question.
Electrons are being pushed around, that requires work. And the electrons experience friction as they move around, needing more energy. If you want to push electrons into a PNP junction in order to turn it on, that requires energy. The electrons don't want to move, and they don't want to move closer together. You have to overcome their mutual repulsion. Take the simplest CPU, a single, lone, transistor. Electrons lose energy as they bump around, generating heat. And overcoming the electric fields of attraction and repulsion requires energy.
There's an interesting article on Wikipedia about Landauer's principle which states that, quote, any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computation paths, must be accompanied by a corresponding entropy increase in non-information bearing degrees of freedom of the information processing apparatus or its environment. This means that, quote, specifically, each bit of lost information will lead to the release of an amount kT lane 2 of heat, where K is the Boltzmann constant and T is the absolute temperature of the circuit. Still quoting. For, if the number of possible logical states of a computation were to decrease as the computation proceeded forward, logical irreversibility, this would constitute a forbidden decrease of entropy, unless the number of possible physical states corresponding to each logical state were to simultaneously increase by at least a compensating amount, so that the total number of possible physical states was no smaller than originally, total entropy has not decreased. So, as a consequence of the second law of thermodynamics, and Landauer, some types of computations cannot be done without generating a minimum amount of heat, and this heat is not a consequence of internal CPU resistance. Cheers!
To add to the other excellent answers, figures you usually see indicate that only a percentage, albeit a large one, of the power consumption ends up in heat. However, what exactly does happen with the rest? Actually, almost everything ends up in heat. By the law of conservation of energy, all the energy, which is power multiplied by time, has to end up somewhere. Almost all processes inside a computer end up turning the energy into heat, directly or indirectly. For example, the fan will turn energy into moving air, equals kinetic energy, however the moving air will be stopped by friction with the surrounding air, which will turn its kinetic energy into heat. The same goes for things like radiation, light from the monitor, radiation from all electrical components, and sound, noises, sound from loudspeakers, a computer produces, they too will be absorbed and transformed into heat. If you read of a percentage that ends up in heat, that may have referred to the power supply alone. The power supply should indeed turn a large percentage of its input into electrical power, not into heat, though it does produce some heat as well. This energy will then be turned into heat by the rest of the computer SMILE.
I am a CPU designer. Let me provide a simplest explanation I can think of. All electrical energy is converted into heat. You may ask, if all electrical energy is converted into heat, who provides energy for computation? All electrical computation dissipates heat energy. In a CPU, or any other semiconductor circuit, electrical computation needs two things. A way to send information from one place to other, think wires. A way to act on information, think transistors. Wires in real world expend heat energy because they have non-zero resistance. Transistors also expend heat energy because electrons, and holes, bump into each other and atoms causing heat. You may now ask, so my electric burner expends all electrical energy as heat but it doesn't compute. Why other way is true, computation expending heat energy. This is because electrons flow in the burner randomly with no specific path, not useful for computation, but in a CPU electrons flow in a precisely defined path, useful for computation, dictated by HW/circuit design. Either way, electrons move around, causing heat dissipation. In other words, the only difference between a burner and a CPU is that former has no specific electrical pathways for electrons to flow and latter does. Just because electron pathways are different, it is not a reason for latter to expend less heat energy. Let's continue hypothetical questioning. Can we pick something very different from puss and see how they contrast? Let's imagine a parked car on road. If I push the car forward, the work done by me, the energy supplied by me, gets converted into two things: A, car's new momentum, and B, heat due to tire/road friction. Wait a minute, you say, car's momentum. Something physical I can see which happened solely because I expended energy towards it, minus heat/friction. The heat from friction is lost, just like CPU heat, but momentum generated is still useful, say charging electrical battery in the car during regenerating braking. CPU's usefulness is in operating on some information, a certain arrangements of bits, and generating a set of new pieces of information, input and output binary bits. Information is abstract though, not physical. Car's usefulness is in physical world. Information is for CPU while physical world is for cars. Both radiate heat when they do something useful for us, but cars do one more thing, they physically move us around. What does CPU do in physical world beyond generating heat? Nothing? Just another way to see how PUS convert all electrical energy into heat and nothing else. Wait a minute, this actually means, I can use PUS as burners? What if my electrical burner is instead a CPU and I put a cooking pan over it to cook dinner? You bet! You get two things, food and information computation with same energy cost. Just very expensive burner though.
If you want to support the channel, please consider subscribing.